Our next speaker is Venu Govindaraju. He's a distinguished professor at SUNY Buffalo in the Computer Science Department. He's an ACM fellow, fellow of the IEEE, fellow of the International Association of Pattern Recognition, and as well as the American Association for the Advancement of Science. He's an expert in handwriting recognition, and his stuff is used for recognizing handwritten postal digits, which is very important. If you don't do it well, that means that someone in the mail sorting facility has to read the envelope manually. So if you have a good algorithm, you can cut costs quite significantly. So very interesting research, and the CCC consortium said that this algorithm is, quote, is one piece of computing research that has changed the world. So without further ado, give the floor to him.
Okay, good afternoon. And so the title of this presentation is Making Sense of All Things Handwritten, a Shakespearean poetic title, All Things Handwritten, from postal addresses to tablet notes. And this once again is kind of an outlier, but this session seems to be about outliers. So we'll see, we are talking about streaming data over here. And as we go along in this talk, you will notice that we are also talking about analog streaming data. That means mail stream, actual physical mail pieces coming, and how the volume is very large and how do you deal with it. So in pattern recognition, when we talk about OCR or optical character recognition, we are mostly talking about printed text. When we talk about handwritten, it's about hand-printed isolated characters usually, and then you also have checkbox, optical mark recognition, and so on. So my talk today is about actual unconstrained handwriting. Okay, and handwriting we feel has come back. For a while people said, even kids in schools are typing most of the time. You can see how they write; it's very sloppy. Handwriting is going to become irrelevant soon, but thankfully for researchers in my lab, we feel with the tablets coming back, handwriting is also back, because for the tablets it's going to be much more convenient to actually write rather than type on that screen. So it's kind of a strange twist, with advancing technology. And also, there are a few articles which talk about how handwriting is actually good. And it helps kids, it trains them in different ways when they actually learn to write properly. Okay. So when we talk about handwriting recognition, unconstrained handwriting is something like this. And today we definitely do not have the technology to actually read what is written, but we can quickly see that it's signed by Albert Einstein. Okay. So humans can still do much better than what machines can do. And since that was Einstein's handwriting, you can take a guess on whose handwriting this is. This is Newton, and once again we don't have technology to transcribe pages like these. Okay, this is supposedly Washington's handwriting, George Washington's. So since he was the president, it's probably his secretary's handwriting, and you can see it's neatly written. And here we have some hope of actually reading if we have some idea of the vocabulary. Now, if you thought those three were difficult, this can be really challenging. This is a doctor's handwriting, right? So, it's maybe the doctor himself doesn't know what he's writing. It's illegible most of the time. Well, that said, in our lab, we have had tremendous success in reading postal addresses. And I'm not sure if you know this, today in the United States, 97% of all mail, whether it's machine typed addresses or handwritten addresses, is completely read by a program. no human being is actually reading it and putting it in different boxes. Okay, so the address image is processed. So this is just an example of an envelope. That's the address. So the first task is to find where the address is. And this itself can be quite challenging if you have magazine covers and the addresses with graphics and so on. And given that address block image as input, the output is actually a 9-digit or 11-digit barcode. Okay, so that is the 5-digit zip code. Then there is a 4-digit add-on which gives you the block, and then 2 more digits give you the precise destination point where that envelope must reach. So the address interpretation task is to take a handwritten block such as that and generate that 11-digit code automatically. And the US Postal Service today can do this for more than 96-97% of the mail, even for handwriting. Okay? And we had something to do with this technology, and I'll talk about that briefly, and I'll connect how we developed machine learning algorithms to solve several sub-problems of this address interpretation task.
Question.
Yes.
So does that can I ask a question now?
Yes, sure.
So does that barcode, does that correspond to like a lat long? Can I put that in a GPS system?
I don't know how it corresponds to the GPS. I don't think it's a latitude, longitude kind of a thing. That 11-digit code, so that you have a zip code, right? A 5-digit zip code. For that 5-digit zip code in that particular area, there is a 4-digit which describes a block of several apartments or houses, okay? Small area. And then the last 2 digits of the street number, 5 plus 4 plus 2, gives you a unique 11-digit destination point code. So every address in the United States, and there are about 250 million destination points, all of them have a unique 11-digit code. Okay, so I don't know if it corresponds to
the unique destination point is the same thing as an mailbox?
Yes, right. So that's what I think. Okay, so here is how the remote computer reader for the Postal Service works. So every day, and you can check your own mailboxes, while the Postal Service has not been doing well and it's been in the news for the wrong reasons, even today, you go to your mailbox, there will be a half a dozen mail pieces in the mailbox, right? There's advertisement and, all kinds of magazines and so on. And occasionally there is a handwritten envelope over there, which is actually the interesting mail piece. But you have several mail pieces in your mailbox every day. In any given city, like I'm not sure of the numbers over here, but in Buffalo, New York, overnight you could have more than 1 million pieces, okay, in Buffalo City. So in the country, about 500 million mail pieces are going through the different post offices around the country. So that's a lot of mail. And this happens every day. Okay, so every day that mail has to be cleared and sent to the various destination points so that there is room for the new mail to come in. So in any given post office, what is done is at a very high speed, about 13 pieces a second. So there's a conveyor belt and the mail is flying by, and there's a camera on the top which is taking pictures of the address face at 13 pieces a second. Okay. Now, by the time that mail reaches the end of that belt, a decision has to be made whether you have actually read that address image and know where it should go, or you need more time to process, so you keep it aside, you spray a fluorescent barcode on the back of the envelope. Sometimes you would see a pink, yellowish, orangish code. So you keep it on the side. The image is then sent to different cities in the country where there are tiers waiting. So maybe a Buffalo image comes to Seattle because there are tiers waiting in Seattle. The image is flashed on the screen, the tiers type the address, the corresponding 11-digit is computed, sent back, and on that same mail piece, the barcode is sprayed. Okay, so there is human keying involved. So when we have automatic recognition of these addresses, fewer and fewer keyers will be needed. Okay, so that's where the savings are. So we started this technology of handwriting address interpretation about 15-16 years back, and you can see how in 1996, 0% of handwritten mail was actually read by a program. It was actually always keyed in by humans. And then we made progress, and you can see like 40%, 50%, and so on. And today, as I mentioned, about 96, 97% of the mail is completely read by a program. That means it reads the zip code, it confirms the city name, it reads the block, street name, and street number, generates the 11-digit code. Now, this has actually saved the Postal Service hundreds of millions of dollars over the years. By some counts, more than $1 billion, because of this technology. And this was fielded, throughout the country by Lockheed Martin, which was the vendor which took our software initially and integrated it into their system. Now, what was the key to this success? So there are several machine learning algorithms and sub-problems that have been solved over here. The key to success was, I explained to you how the pattern recognition task is one of taking an address block image as input, and there are 250 million classes, because it can go to any one of those destination points. And then you break down that problem and you say, okay, if I know the zip code and if I know the street number, what are the possible street names in that block? It turns out that on average, there are only about 15 to 20 street names once you give me the zip code and the street number. So the handwriting recognition problem then is to take the street name image and match it against those 15 or 20 different street names. Now this lexicon of 15 to 20 names is dynamically generated, because every time you change the zip code, there is a different set of 15, 20 names. So it's not a static lexicon like, say, in the bank check problem. In the bank check problem, you always have the same words appearing in the legal amount. 1, 2, 50, 100, for some people in Silicon Valley, millions, billions, but for most of us, there are only about 30 or 40 words, right? But that is a static lexicon. Here, the lexicon is dynamic, okay? So you can see in this case, 14213 was recognized because the numeral recognition problem is easier. You have only 10 classes. Then the 74 is recognized. Looking at using those two, you have a postal directory lookup, and that's the list of possible streets. So all those streets are matched against the snippet of the street name, and then the recognition says it is Livingston Street. Okay. So if you look at the tasks in the address interpretation, there are a whole bunch of AI tasks. So we have to figure out address versus non-address, machine printed versus handwritten. Character recognition is a 10 class, 26 uppercase, lowercase, and so on. Dynamic lexicons for word recognition and address encoding. Now I put up this slide because 15 years back, when we presented results of our word recognition algorithms, we would present this table, and I have taken this from a presentation I made 15 years back. And take note that we would report how much time it took the neural network to be trained. So students would set it up over the weekend and then go home, and then the network is trained. And that was an important thing to look at, right? Because if you're going to make modifications to your algorithms, that could be the bottleneck. And speed was always important. So you will notice that in certain cases it was several hours. Okay. Now what has happened is, over the years, because of various technological improvements, things have changed, and I'll talk about that in the next few graphs. This chart is to show that in the system that was first delivered in 96, 97, there were a whole bunch of heuristic rules. Okay. It was like an expert system. So we would have rules like, if the first recognizer gives you a score greater than this, then accept it, otherwise send it to another recognizer, and if the score, and rules of if, then, else, and so on. Now, all those things have changed now, and we have sophisticated machine learning algorithms. Given the data and given the speed that we have with the processors, the algorithms have changed, and we have actually benefited, and we have moved from the 20–30% recognition rate now to the high 90s. I don't have too much time, for doing this talk fully. 5 minutes, okay. But these are the kinds of heuristic rules you would see in the code which was actually running. By the way, this system that we delivered to Lockheed Martin for deployment throughout the country was developed in our lab. Code was written by our students, and it was given as is, as object libraries, and deployed. We were like this when it first went out in the field, but it worked. Okay, so that is something to say about students writing good code. So looks like I have to jump through several slides here. So what I wanted to show was, so these are the kinds of sub-problems you need to address when you're talking about this address interpretation. So there's pre-processing, handwriting recognition, classifier combination, a whole bunch of, there are other talks also on this. Classifier combination, for the same problem, you have a neural network, an SVM, or some HMM or other methods. How do you combine these results? So we have some good machine learning algorithms for combination of classifiers. And then now we are looking at search. Today, on the Google search box, when you type in keywords, all that is coming back is text documents or printed documents, PDFs, right? Unless a handwritten document is tagged with those keywords separately, you cannot actually pull back because there is no handwriting recognition that is taking place. And we want to change that. That's part of our research, developing machine learning algorithms for that. I'm just going to just show you some results. We have a machine learning algorithm for doing the binarization. That's the MRF approach. Removing lines, again, a machine learning algorithm for that, which does better than all those expert system style rules. Even for simple problems like take a document and tell me where are the handwritten components, where are the machine printed components, and where are the overlapped ones. We have some nice machine learning algorithms to do this. Okay, I don't have time, so I'm going to jump through this. There's too much material here. We have been able to look at this is doctor's handwriting and prescriptions. We have been doing quite well actually, but they still don't trust our recognition with people's lives, I guess. It's one thing to get your neighbor's mail in your mailbox and totally different, when it comes to medicines. But we are working on these. So you can see some of these, it's very difficult even for us to read. So unless you have the context and you know what these medicine names are, you can't, but our recognition is pretty good because it's looking at the lexicon. And okay, I had some slides on how we actually do this recognition. I think I'll just present this slide and close. So what we are doing is we have an interactive model for this handwriting recognition. So we looked at how we have a dynamic constrained lexicon. At any given time, I have an image and I have a small lexicon. So handwriting recognition for the computer is all guesswork, okay? So this is just like doing multiple choice questions in exams. You may not know the actual answer, but once you look at the choices, then you do some elimination and some guesswork, and suddenly you are doing as well as the best student in the class because you're able to guess quite well. So look at this. If I look at that profile of that word image and I ask you to guess which word US city name it is, you may not be able to tell me, but once you look at the choices, you say Amherst, Buffalo, and Boston. Well, Amherst doesn't have a descender, and Boston doesn't have any descender. This image has descenders. Buffalo matches because you have two F's, it must be Buffalo. So the way the recognition happened over here was, we look at the image, extract some features, go to the lexicon and see which features would match, eliminate some of the choices, look at the remaining choices and say which features should I extract now to tell them apart, go back to the image, and so back and forth, just like you would do a multiple choice question. And of course, as in all multiple choice questions, once you have none of the above, it becomes tricky, okay? So there's too much information here, but the other thing that we looked at was coming up with good machine learning algorithms for combination of classifiers. Previous methods have been about fixed rules, so they would look at max rule, min rule, majority rule, and so on. We have done work where we can look at what function actually will be optimal in different scenarios, and also how do you use the scores. So each time a classifier comes back with a confidence value. So can you use that confidence value in your combination? So we have done some work in that. Boy, I didn't realize that it would fly so fast. I'm just closing up. So we have done some work on transcript mapping, where you might, for historians, where some historians might have actually transcribed manually some historical documents, and then we look at the images of those documents and the transcription and do a mapping so that then you can go and hyperlink some of those images. Do some enhancements such as these. Okay, and then the latest thing that we are working on is on tablets, where you might take a picture of something and say, can you show me more like this? I want to buy this. And then you might just write something on the tablet saying tennis racket and the Wilson. So that's what you're looking for. Okay. And okay, this is the last one. We are also looking at captures, handwritten captures, because today, if you have seen, the machine printed captures are getting so difficult. I take 3-4 tries nowadays, to get in. And I think after a while there must be something which says after 5 sincere tries, let him come in. So we are looking at handwritten words, and we are doing things like this where you have to read the sentences. She teaches us English. What does she teach us? It's so easy for us to say English is the answer. It involves handwriting recognition. It involves natural language understanding. So we are working on some of these ideas. Thank you very much.
That's a fascinating corporate work. Are there any questions in the audience?
So the government just released the 1940 census, which was a bunch like 200 million names handwritten, and you can't find anybody because it's not digitized. So I'm curious if they come to people like you looking to automate handwriting from 1940.
Right, I mean, they haven't come to us yet, but for census forms, people have been looking at using, automated techniques, because in the census forms, one thing is the names, the other thing is the professions, and there's a list, it's a limited list, right? It's not going to be very large, and then you can correlate it with the previous census and so on. So there is some constraints. As long as you have some constraints to bring the lexicon size, make it small, so that you can have that interactive, going back and forth, then this problem is tractable. If it's completely unconstrained, like you saw Newton's writing and so on, it's going to be difficult. But census forms, I think that's a tractable problem.
So I wondered over the years about desk representations for things like characters, cursive characters, and so on. I think it's what's not used, but potentially interesting, and many people propose this over the years, is essentially a time series representation, which we heard about the first time, where you now turning right, accelerating, and so on, as opposed to pixel, image-based kind of.
Right. I mean, the time series methods have been actually used in online handwriting recognition, where you have the sequence, the time series is there, right? So it captures the pen movement as the hand is moving. So you have the X, Y, and T. So for those online applications, people have used those. This is all offline. And for offline also, there have been papers where they have tried to retrace, the movement of the pen and then use that representation, but they haven't been that successful.
I was just curious how many different classifiers you have actually trained.
Okay, for the word recognition problem, that means give me a street name and give me a lexicon. So the system that you put out in the field had 3 recognizers, and they all approached the problem in different ways. One was lexicon driven, the other was lexicon free, one was looking at holistic features. And for digit recognition problem, we had again about 3. One was a neural network based, and one was a nearest classifier, nearest neighbor based, and so on. So they were all combined.
Although we have time for one more question before you shuffle out, we're going to start again at 9 a.m. The food's going to start at 8 a.m. So 9 a.m. is the first talk. Okay.
Has this been extended to non-English handwriting?
Yes, absolutely. So right now we are working on a project for DARPA, which is for Arabic handwriting recognition. And we got an NSF grant for looking at Devanagari, which is the Indic scripts. So yes, we have been trying to, but it's a different problem, right? Because in English, the cursive writing makes it very difficult to do segmentation, in Arabic as well. Arabic is also cursive, and it's very difficult to do the segmentation of characters.
Let's thank the speaker. Read the envelope manually. So if you have good algorithm, you can cut costs quite significantly. So very interesting research, and the CCC consortium said that this algorithm is, quote, is one piece of computing research that has changed the world. So without further ado, give the floor to him.
Okay, good afternoon. And so the title of this presentation is Making Sense of All Things Handwritten, a Shakespearean poetic title, All Things Handwritten, from postal addresses to tablet notes. And this, once again, is kind of an outlier, but this session seems to be about outliers. So we'll see, we are talking about streaming data over here. And as we go along in this talk, you will notice that we are also talking about analog streaming data. That means mail stream, actual physical mail pieces coming, and how the volume is very large and how do you deal with it. So in pattern recognition, when we talk about OCR,
our next speaker is Venu Govindaraju. He's a distinguished professor at SUNY Buffalo in the Computer Science Department. He's an ACM fellow, fellow of the IEEE, fellow of the International Association of Pattern Recognition, and as well as the American Association for the Advancement of Science. He's an expert in handwriting recognition, and his stuff is used for recognizing handwritten postal digits, which is very important. If you don't do it well, that means that someone in the mail sorting facility has to
also back, because for the tablets it's going to be much more convenient to actually write rather than type on that screen. So it's kind of a strange twist with advancing technology. And also there are a few articles which talk about how handwriting is actually good and it helps kids trains them in different ways when they actually learn to write properly. Okay. So when we talk about handwriting recognition, unconstrained handwriting is something like this. And today we definitely do not have the technology to actually read what is written, but we can quickly see that it's signed by or optical character recognition. We are mostly talking about printed text. When we talk about handwritten, it's about hand-printed isolated characters usually. And then you also have checkbox, optical mark recognition and so on. So my talk today is about actual unconstrained handwriting. Okay, and handwriting we feel has come back. For a while people said, even kids in schools are typing most of the time. You can see how they write, it's very sloppy. Handwriting is going to become irrelevant soon, but thankfully for researchers in my lab, we feel with the tablets coming back, handwriting